Hello and welcome to a lesson in Calculus 2. Today's topic will be delving into the world of parametrics. So let's get started. So today we're going to be looking at how we can use calculus to manipulate parametric equations. So if we take a second to review what exactly are parametric equations, if you remember from your pre-calculus class, parametric equations are where you have usually two individual functions that are defined by a parameter, and the most common parameter you'll see is t, and usually the functions are x of t and y of t, which are defined in pairs to give the points of certain graphs. And this differs from Cartesian equations because Cartesian equations are usually defined by one function, whereas the parametric curve is defined by two functions. So up in the right hand corner you can see the parametric functions that I've just provided as an example to refresh yourself on what parametric equations look like. So today let's just talk a little bit about our lesson objectives. So for this video, what we want to do is we want to, one, be able to understand how we can manipulate parametric equations using calculus, so that means differentiating and integrating them, because it can be done. And then we can actually take this knowledge and apply it to some very interesting concepts, which actually hold a lot of real-world merit in terms of particle movement, in terms of concepts such as acceleration, velocity, speed, displacement, all sorts of things along those lines. And ultimately our goal for the video is to achieve fluency in this topic, because on the AP exam it's going to be very important that you become fluent in this topic. So I hope that this video sets you on the track to fluency. So let's dive right in. So let's look at some basic derivative formulas, which are very important in terms of parametrics. So first we are given a parametric pair. So if x of t and y of t are defined, then what we can do is we can differentiate both of these independently. That is, we can take dx dt and dy dt, and this simply follows the same format as how you would differentiate a Cartesian equation. You could use the power rule, chain rule, etc. All those formulas still apply. So it's very simple, and I'm not going to delve into how to do that because that's self-explanatory, but I am going to talk about how to differentiate y in respect to x, which can be done in parametric equations. So let's look at the first derivative, dy dx. So the first derivative is defined by dy dx is equal to dy dt over dx dt. So you're simply differentiating both parameters individually, and then you're dividing y over the derivative of y over the derivative of x, which is pretty simple. Now let's take a look at the second derivative, which is a much more complicated. So the second derivative is, as we remember from the beginning of the year, is simply the derivative of the first derivative itself. So that's that is simply dy dx derived, and that in terms of parametrics simplifies to the derivative of dy dt over dx dt, because that's simply substituting the equation above in for dy over dx. And finally, doing complete simplification, what we get is that the second derivative is equal to the derivative of dy with respect to x divided by dx over dt. Now this is, and so in this video I'm not going to go into the expanded proof of how to achieve this formula, but if you would like, just to save time, but if you'd like to see that, you can check out other videos. So let's go on. So now let's do a little bit of quick practice just to reinforce the notions that we've just talked about. So let's take a parametric function defined by these two parameters. So we have x of t is equal to 6t cubed minus 3t squared, and y of t is equal to sine of t. Okay, so now we're asked to find a, the first derivative with respect to x, and b, the second derivative with respect to x. So we're going to have to apply the formulas that we just learned. So to start off on the bat, to find the first derivative, we're going to need to independently differentiate x of t and y of t. So let's take dx over dt, which is simply using the power rule, and we get 18t squared minus 6t, and then dy dt, which is derivative of sine is cosine of t. That's a known derivative, and so combining them, we need to divide dy dt over dx dt, and dividing that, we get cosine of t divided by 18t squared minus 6t. Very self-explanatory, I think. And now we're asked to find the second derivative, which is a little bit tricky. So first we need to remember the two parts. First, on the top, on the numerator, we are taking the second derivative with respect to x, and then on the bottom it's simply dx over dt. So let's find that the numerator first. So the derivative with the derivative of the derivative with respect to I'm sorry, I accidentally made a mistake in the formatting of this. Before it read dx over dy, so I just changed that to dy over dx, which is the correct way it should read. So we're taking the derivative of the first derivative with respect to x, which is basically doing a quotient rule of the first derivative right above there. So I'm not going to go into a detailed explanation of how to do the quotient rule. This is simply for you to check your answer. If you need help with the quotient rule, please see a previous video. But that is the correct expansion of the top. So now let's move along, and over here, just for your reference, I'm going to rewrite quickly. I'm going to rewrite the problem parameters. So those are the function. So now we have the first derivative of both with respect to t, and now let me rewrite the derivative of the first derivative. So now let's recall that we need to divide what we solved over here by dx over dt. So I'm going to rewrite that expansion, and instead of dividing by dx dt, because it's a fraction, we can just multiply it by the reciprocal, which is simply multiplying multiplying this the expansion on the left by 1 divided by 18t squared minus 6t, and that's the correct answer in non-simplified form. So now we can use this information to look at parametrics in light of particle movement. So let's just start off with a basis. If we have the parametric equation, which is defined simply by the coordinates x of t and y of t in vector form, then we can find the velocity vector of this parametric, which the velocity vector is simply given by dx dt and dy dt respectively in terms of the point. And then again we can take the acceleration vector, which is simply, drumroll please, the second derivative with respect to t for both of those parameters, which is very simple. And it makes sense if you think about what you've learned at the beginning of the year in terms of particle movement, and how the acceleration is equivalent to the second derivative, the velocity to the first. So now let's look at the third thing we could do, which is speed, or the speed is the magnitude of velocity. And in this case, the speed would be it is the square root of dx dt squared plus dy dt squared. And that's simply something that just needs to be known. And in addition, we can find, fourth, the position vector of the particle. Now this is a little trickery because we have to solve independently for the x coordinate and the y coordinate, and we need to integrate in this terms. So first what I'm doing is I'm integrating both points. So what I'm doing here is I'm integrating from a to b, which is a defined parameter, of the first derivative dx dt of the x point and dy dt of the y point, and then I'm adding onto them the initial condition defined by the starting point of the integral, which is in this case x of a and y of a. So that's the initial condition, and that will give us displacement plus the starting position, which will give us the final position at point B. So, and it's also important to note that the position of the particle is given in vector notation, where the x position is defined by the top integral and our y position is defined by the bottom integral. And lastly, we can look at total distance traveled over an interval, and this is simply over the interval a to b. This is simply defined by the integral from a to b of the speed, which is simply the square root of dx dt squared plus dy dt squared dt, and that gives us distance traveled over an interval. So it's interesting to note that all of these formulas are related if you think back to the fundamental theorem of calculus. We can apply the same notions that we learned to Cartesian equations in terms of particle movement to parametrics. So we have a defined parametric where we can differentiate it to get velocity, and again differentiate it to get acceleration, and vice versa. We can integrate that to get position and displacement as well. So I think this is truly wonderful to see the connection between these two concepts. So now let's take a look at an FRQ practice question. So here we've got this problem stated above, so I will give you a second to read the problem. I would pause the video here to read the problem. Just to save time, I'm not going to do that. So now, alright, so pause the video. Alright, so now let's dive into this problem. So first it asks to find the speed of the particle at t equals 3. So the speed of the particle, when you hear that, you should automatically snap in your head the speed equation, which for this case is simply the square root of dx dt squared plus dy dt squared. And we're evaluating at t equals 3 because that's what the question is asking. So evaluating at t equals 3, of course this is a calculator question, and I'm using a calculator. So you would solve that square root, and you would, evaluating numerically, you would get 13.007. Now the second part of the question, is asking to find the acceleration vector of the particle at t equals 3. So all we simply have to do is take the second derivative with respect to t for both parameters and put that in vector notation, solving at 3. So evaluating numerically, we get that, and evaluating numerically solving, we get 4, negative 5.466, and that's the acceleration vector. So let me just put that back up there for you. So now part B. It's asking for us to find the slope of the line tangent to the path of the particle at t equals 3. The slope of the line tangent to the particle is simply dy over dx evaluated at t equals 3. So this is simply sine of 9 over 13, or 0.031. The way I found this is I simply plugged in 3 for both those independent derivatives up there, dx dt and dy dt, which are already given to us, which is a huge time saver, so don't, and that's how I found dy over dx, which is very simple. So for part C, it's asking for the position of the particle at t equals 3. This is a little complicated, and it's going to take longer because we actually have to solve those two integrals in terms of x the integral of the derivative of x in terms of t. Here, I'll write it out for you. So we're doing from 0 to 3 the integral of x with respect to t plus the initial condition at 0 because it's 0 to 3. And then we're doing the integral of y with respect to t plus the initial condition at 0. And on the right in the red, you can see that I've simply plugged in all of what you need for this problem. So now let me just rewrite it at the top for you to see once again, and I'll quickly rewrite that very quickly. So now, of course, this is a calculator problem, so you can evaluate these integral on your own, and by evaluating this integral on your own, you can see that you get 21 comma negative 3.226, and that's expressed in a vector form because it is position independent position. And lastly, what we need to do is we need to find total distance traveled, which total distance traveled is simply the integral from, because it's from 0 to 3, the integral from 0 to 3 of the speed equation, which is dy dt squared plus dx dt squared. And evaluating numerically in terms of our problem, we get sine t squared plus 4t plus 1 squared. And evaluating that integral numerically, it is 21.091. So lastly, let's just quickly talk about, in closing, what we've learned today. Our first objective, we learned how to manipulate parametric functions with calculus. And secondly, we learned how to apply these formulas in terms of particle velocity problems, and we gained fluency. And by particle velocity, I mean in total acceleration, speed, etc. We learned how to apply the fundamental theorem, essentially, to parametric calculus. So I just want to say, great job. I hope this video helped you. If at all you need to contact me, you can find my contact information below. And I wish you the best of luck on your calculus endeavors, and so long.